This is Unit 3, Video 6. In this video we will discuss molecular geometry. Now this is what it sounds like, the shape of molecules. So we'll talk about its shape, its bond angles, its bond distances, and so forth. There's a lot to talk about in terms of these molecules. And the theory that will get us there is called Vesper Theory, or the Vesper model. It's pronounced Vesper even though it's spelled separate. And this is an acronym standing for valence shell electron pair repulsion. What this says is that each of the electron pairs, so if you have a Lewis structure, because we have to work with Lewis structures, in this case, here is the Lewis structure. What it says, and each of these chlorines obviously has an octet. We can fill that in. We're going to focus on the central atom. And what we realize is that each of these electron areas is negatively charged. And so all of these electron areas will repel one another. And so they will arrange themselves in a way to be as far as possible from each other, because they are electron areas and electron densities that repel one another. So for example, if around carbon you have these 4 electron areas, these will go to 4 distant locations as far as they can in 3 dimensions. This is in 3D. And they will form this shape. This is actually called tetrahedral, and we'll talk about this more. Tetrahedral is actually one of the most common shapes of molecules. And that's how this Vesper model works. It's valence shell because these pairs that we have been drawing in Lewis structures are actually valence electrons. Alright? Now, let's define a few things. Let's define something called an electron domain. So we can refer to these electron pairs, whether they're bonded or unbonded, as electron domains. So for example, this could be called an electron domain, so can this, and so can this. Here it says that a double or a triple bond actually counts as one electron domain. So this double bond here counts as one domain, and domain meaning area of electrons. So this is one area of electrons, here's another area of electrons, here's another area. So in this you actually have 4 areas of electrons, or 4 electron domains. Notice we counted the unbonded pair and the bonded pair and the double bond as just one electron domain. You'll also notice that A here is an atom that has an expanded octet. Right, these are electron domains. We can then determine the electron domain geometry. In other words, the shape just in terms of those electron domains. So in the case of this structure, if you take a look, we have 4 domains total. We have 1 unbonded and 3 bonded domains. Now these will go as far as they can from each other, creating this familiar structure called a tetrahedral arrangement. So the electron domain geometry, or the geometry in terms of just electron domains, will be tetrahedral. And this comes, as you'll see, from the shape that it forms. This is a tetrahedron, a 3-dimensional 4-sided figure. And essentially each of these electron domains go to an opposite corner of this tetrahedron. And that's what essentially it looks like. Now, if we consider just the atoms, in other words, if we ignore the electrons, then we have this geometry. We have something called trigonal pyramidal. Now the electron pair is still up here influencing the rest of the bonds, and in fact what's happening is it's pushing the rest of these bonds down, creating what's called a pyramid. Essentially that's why this shape here, structure, looks like a pyramid, and that's why it's called pyramidal. So within each of the electron domains you will see there'll be 1 or more molecular geometries. So we'll actually distinguish between electron domain geometry and then molecular geometry. And we'll talk about 3 categories to begin with. So the first geometry is the linear electron domain geometry. And the linear one has 2 electron domains. In this case you have the atom A, and you have 2 electron domains, one to the left, one to the right. And obviously for these to go as far as they can from each other, they'll form this linear structure. Now if you have atoms at the end of it, in this case you have 2 atoms at the end, then the molecular geometry. Now remember, we're going to begin with electron domain. This is the electron domain geometry, and then we're going to determine the molecular geometry. In this case, it's the same, because you simply have atoms on the end of the electron domains. So this is linear. Simplest one. And by the way, down here it says, note that if you only have two atoms that are bonded, and this is common, for example, if you have carbon monoxide or if you have oxygen, carbon monoxide has a triple bond, oxygen has a double bond, and so on and so forth, you obviously have linear geometry. I will actually show you an example of this. This here, an example of it is famously CO2. Carbon dioxide will famously form this linear electron or linear molecular geometry because you only have two electron domains that go as far as they can from each other. Good. The second one that we'll talk about is trigonal planar electron domain geometry. So if you have three areas, here you have an atom, and if you have three areas of electrons around that, it'll go to three opposite directions and give you a triangular plane. This is called trigonal planar because technically all three of these, here's A, all three of these lie, you can say, in a plane. So if I kind of try to draw them in a plane, they'll look like this. They'll lie in a plane. I don't know if that helps or not. But then we have two possibilities that arise from this. If all of the electron domains have bonding atoms, in other words, if you have three atoms on the end, then you keep the same geometry. This is still called trigonal planar, just like with the first one. If, however, one of the atoms is missing and all you have is an unbonded pair or non-bonding pair, then you have something called bent. Now it's bent because essentially this electron domain pushes these bonded pairs downwards, creating a bent structure. An example of this would actually be SO2. So if you draw the structure of SO2, it looks like this. If you want a full octet and all the oxygens, it looks like this. Now what happens is this exhibits resonance, so both the left and the right bonds are actually the same. But what you get is you have this unbonded pair that pushes the rest of these down, creating the bent structure. And the whole geometry, the whole molecule actually just looks like this. If you were to see it, the molecule has this bent shape. And we'll see this a little better with three-dimensional models. Right, so this is the second category, and the third category is this very famous one called tetrahedral. Now, we'll begin then with four electron domains. Like we have an atom here, and we have four electron domains. Here's one, here's two, here's three, here's four. And in 3 dimensions, you can see that they go to opposite sides to try to minimize their repulsion. And this is called tetrahedral. And again, it's called tetrahedral because it creates a 3-dimensional figure called a tetrahedron that has 4 faces. Here's one face, here's another face, there's a bottom face, and there's a face on the back. So that looks a little confusing, but it's a 3-dimensional, look it up, a 3-dimensional 4-sided figure is a tetrahedron. Now, if you have atoms in all of these electron domains, all 4 of them have atoms, then you simply call this tetrahedral. The most common one, tetrahedral. The famous tetrahedral structure is essentially carbon with any 4 atoms at the end. Could be fluorine, could be hydrogen, could be chlorine. Usually they are halogens or hydrogen. So this gets you a tetrahedral arrangement for the molecule. Now, if one of the domains, as in the case here, does not have an atom, then you get something called trigonal pyramidal. And it's essentially a triangle that's a pyramid. It has a pyramidal base. It has a base that's a triangle. And an example of this famously is NH3. If you draw NH3, here's what you get. You actually have a non-bonded pair of electrons, which then influences the rest of these bonds, pushing down on them, creating this structure. So in the end, the NH3 molecule actually looks like this. If you were to look at it, it just looks like a pyramid in 3 dimensions. If you have 2 of them being non-bonding, like in the case here, these 2 are non-bonding, they don't have an atom at the end of them, then you get the bent shape again. Now we've seen bent before, so you can get bent 2 ways. You can get it from tetrahedral, you can also get it from the previous one, which is trigonal planar. And in this case, what you see is you see this bent structure. This is the famous water. Water has this structure. So if you draw a structure of water, it looks like this, with a pair on top, with a pair on the bottom. And this is the most confused structure because most students want to say that this is linear. It looks like it's in a line. However, in 3 dimensions, these 4 electron domains separate as far as they can, creating a tetrahedral pattern. And then if you ignore 2 of them, or if you rather say that 2 of them don't have atoms, then you get this bent shape. Now it turns out it doesn't matter which 2 you put atoms on. Like if you were to put atoms on this one and on this one, you'd still get this bent shape. You kind of see it still forms this bent shape. And again, this will be a little more easily seen when we do this with three-dimensional model. Alright, let's try an example and then we'll finish the video. So we're going to use this Vesper model to predict the electron domain and the molecular geometries of these three structures. I will draw their Lewis structures really quickly. Pause the video if you want to try them on your own. But Cl2O should have this structure. Remember, you're drawing the Lewis structure to make sure that you have a total number of electrons that matches the number of valence electrons they brought. And in this case, here's the structure you come out with. Now, in this case, what we do is we first assign the electron domain geometry. So the electron domain geometry, which is the first one that we look at, is based on simply how many electron domains around the central atom. It'll always be focused on the central atom. So in this case, we have 1, 2, 3, 4 electron domain geometries, and 4 go to opposite sides, and they make a tetrahedron, so we call this tetrahedral. So the electron domain geometry is tetrahedral. Now then we look at the molecular geometry. And molecular geometry will simply account for the atoms. They'll essentially ignore the electrons. However, the electrons are still there, influencing the bond. Now this is that famous case where if it's tetrahedral, it looks like this to begin with. So here is essentially what it looks like. Here's the central atom. And if 2 of them are gone, if 2 of these are just electron pairs, so we can't really see them even though they're influencing the bond, you get yourself a bent structure. So the molecular geometry is bent. This is actually the same structure as water, essentially. Alright, let's try the next one. The next one is SnCl3. Again, if you draw this, following all the rules, you get yourself this structure. Now, you'll actually notice that Sn is a metal, tin, but it still forms covalent bonds because the difference in electronegativity allows it to do so. You can also put dots all around the outside to make sure you're following the octet rule. I did that incorrectly since it's Cl3, so this actually should be a non-bonding pair. Apologize there. Alright, looks like this. So now the electron domain geometry should be based on how many electron domains we see. We have 1, 2, 3, 4. Oh, we've just seen this. It's again tetrahedral. Alright. And now we consider only the bonds that have atoms at the end of them, just these 3. And then this pair is simply influencing them, and this pair is pushing them down, creating a molecular geometry called trigonal pyramidal. Some say pyramidal. Feel free to say pyramidal or pyramidal. And that's how you get it. So both of these actually come from the tetrahedral electron domain geometry. This last one, this is famous ozone, and we've drawn him once or twice. And what you have here is you get this structure. Again, I'm doing it quickly, but you would follow the rules to make sure you draw it correctly. Now, in this case, you actually have resonance. Remember, anytime you have a double bond on one side that's equivalent to another double bond, you want to show both possibilities, creating resonance. Okay, so now the question is, what is the electron domain geometry? Let's do it up here for ozone. The electron domain geometry, in this case, has 1, 2, 3 areas of electron density, and that is called trigonal planar. This was the second category that we've seen. Alright, now in terms of molecular geometry, we say that only 2 of these have atoms on them, and then this is simply influencing the atoms, pushing them down, creating the bent shape again. This is actually bent. You do small uppercase or lowercase. This is the bent geometry. Notice we've seen bent come from tetrahedral, bent can also come from trigonal planar. Alright, we'll practice a lot of this in class. Go ahead and try the 3 more examples on your own, and this completes video 6 of Unit 3.